is Ben Erichson. I'm a postdoc here in the Department of Statistics, and my research interests are deep learning, dynamical systems, and AI safety. Before we get started, I would like to thank my collaborators, in particular Michael Mahoney, who is my advisor, and Vanessa, Francesco, Charles, and Jeffrey, who are students working with me. I would also like to thank my external collaborators, Alejandro from Google Research, Dane from the University at Buffalo, and Omri from the Ben Gurion University. Well, we all know that neural networks are brittle and relatively sensitive to a range of adversarial environments. And this becomes now an issue as we start to deploy such models in real-world applications such as self-driving cars. So we really need to start to think about how can we improve the robustness of such model, or how can we better leverage some domain knowledge about the problem under consideration. We need also metrics for quantifying the uncertainty in the predictions that we make. And we need new strategies to better deal with domain-shifted data during inference time. To tackle some of these challenges, we try to leverage ideas from dynamical systems. And to do so, we try to break apart a deep neural network into simpler building blocks that we can then study using tools from control theory and dynamical system theory. And in turn, these insights that we generate can then be used to design more robust models. We can also take advantage of the idea of neural differential equations that are easier to study and where we have a lot of knowledge from the theory of differential equations that we can leverage. And then we can also use higher order integration schemes that lead to different computational graphs and that might have nicer stability properties. And to give you a flavor of the advantage of this approach, I show you here kind of different state-of-the-art recurrent neural networks. And I plot the test accuracy as a function of the amount of noise that we add to the test inputs. And you can see that the test accuracy quickly drops as we increase the amount of input perturbations. In contrast, the current neural networks that we propose, which is stable by design and highlighted in red here, is more resilient to input perturbations. Another idea is to use the concept of noise response analysis to measure the robustness of a neural network. Particularly here, we were interested in using noise response analysis for detecting whether a model was trained with a backdoor or without a backdoor. And you can see that backdoor models have kind of somewhat strange behavior. By that I mean that they are very sensitive to even very small input perturbations as compared to a clean model. And kind of these insights allows us to compute what we call a titration curve. And we can use kind of a titration curve as a type of fingerprinting for deep neural networks. And that is important to validate the quality of a neural network before it gets deployed in a real-world application. I think it's really important that we start to rethink how we train, how we design deep neural networks in order to improve the interpretability of such models and in order to improve the robustness. And there are many different approaches how we can tackle this problem. But kind of the dynamical systems point of view is a particularly interesting one that has recently generated a range of interesting results. And here's a short list of some recent work which was supported by CLTC this year. Thank you very much. And if you have any questions, feel free to drop me an email.